That's okay. Okay. Let me first thank all the organizers for inviting me to this wonderful conference, even though I missed the 2009 meeting, but it really gave me a lot of inspiration to attend this conference, and I thank again for the organizers to invite me. Now, this talk is in fact the work of ourselves and Satsma and Grammaticos, Ramani and Mumura, but this consists of two papers actually. Even though we take advantage of my collaboration with the Grammaticos and Ramani, we combine these two results in this talk, and we are going to give the results containing in these two papers. So basically, we are concerned with the linearization, and by that through that means we could able to integrate the systems explicitly. So as it is pointed out by Calogero that integrable systems are both universal and widely applicable. Moreover, linear systems are omnipresent in the domain of integrable differential equations. So he introduced two notions, S integrable and C integrability. So S integrability concerned with systems which could be solved through inverse scattering technique, and C integrability through change of variable and linearization through Koloff type of transformations. So this is now we are concerning with three types of family of linearizable systems. One is projective type. Oh, sorry. Projective systems which can be linearized through Koloff type of transformations, and Gambier system which is represented in terms of coupled Riccati, Riccati with another Riccati, where the coefficient of the first Riccati appears as the solutions of the first Riccati appears as the coefficient of the second Riccati. And third family we call third family, this is a system of nonlinear system together with a linear system. So these three families do not appear in the, especially the third family do not appear in the Penlevet classification because they are not passing the Penlevet property. So the question is whether this can be extended to discrete domain as well. This is absolutely go through the discrete domain, and we can carry out all this analysis of Gambier, projective and the third kind to the discrete domain and linearize them, and we could able to get solutions explicitly also. So Grammaticos et al. Has derived the Penlevet equations, studied various properties including special solutions. Later Sakai proposed a geometric approach wherein he derived systematically all the discrete Penlevet equations. And the main important point is the third one for this talk, because starting with this discrete Penlevet, in this case the higher level, and then take the limits and degeneracies, taking the various limits, and degeneracy limit means taking the parameters to certain limit, we can reduce the systems. Degeneracy means some factorization we expect, then reduce the systems. So these two aspects reduce, we could able to get lot of linearizable systems from these classes with the more general, with the many parameters. So, our point of view is that limit and degeneracy can be applied at the various levels and obtain some new integrable systems, including linearizable one. So, just to recall Riccati equation. A Riccati equation can be linearized, first order nonlinear system, which can be linearized to Koloff type of transformations, and then to linear second order equation. Of course, the solution of this equation is known, therefore, we could able to get the solution of the Riccati as well. In the discrete case, the same thing can be applied. So, consider the homographic mapping and then substitute or introduce yn equal to Pn by Qn, then we will get two equations, one for P and one for Q, and solve one equation, that means P in terms of Q, and substitute this P in the other equation, we get a linear equations in Q. So, therefore, homographic mapping also can be solved through the solutions of these linear systems as well. This is exactly same as Riccati. Now, we consider the 3-point mapping, and again this transformation un by un, like previous case, we can reduce these to linear equations. Therefore, this could be able to solve through the solutions of this linear equation. So, so previous two examples are the examples of projective type. Now, we consider the Gambier type of equations, and in fact, if you solve for xn here, you will get expression like homographic in with the coefficients in yn, and we can bring it these two equations in the familiar form, but for our convenience we just write this in this form. So, indeed this is a homography of two equations in x and y. This is the equations which we call third kind. So, this is very interesting class wherein we consider the nonlinear equations with one parameter, okay, one parameter should be there, and a linear equations. So, you take the discrete derivative of this linear equation, that means you take the upshift and then eliminate this parameter k by taking the upshift of these equations, and demand that eliminate the xn minus 1 xn minus 2 between these upshifted equations and the upshifted f and fn plus 1. Demand that the resultant is vanishing in order to ensure that the compatibility between the linear system and a nonlinear system is okay. So, this is useful to solve the nonlinear system in the following way. That means, start with initial values xm and xm minus 1, and then from the nonlinear system, I am sorry, from the nonlinear system, if you know, to introduce the two initial values here, we can find the value xm plus xm plus 1 in fm, and then use these three values xm, xm minus 1, xm plus 1 in the linear equation, obtain the value of k. Once k is obtained, and solving the confusion is solving this linear system is you see. So, all the variables are known, therefore, k is known, therefore, for all values of x we can solve these linear systems, and since the solutions of nonlinear system and the linear system are the same, therefore, the solution of the nonlinear system is obtained. Now, just briefly recall the QRT mapping, which is well known, of course, very popular, and we have asymmetric mapping and also symmetric mapping, where this x n goes to x to m and y n goes to x to m plus 1, etc. We can reduce the symmetric mapping, and the invariance of this QRT mapping is given by this form and satisfies these conditions of invariance. And for symmetric mapping, we can give this invariant in the following form, satisfies these conditions. Now, the main point is this can be parameterized, invariant can be parameterized, it is well known by in terms of elliptic functions, by reducing the homographic transformations. This invariant can be reduced to this canonical form, and whereby we can parameterize in terms of elliptic functions. And asymmetric case also can be integrated in the similar way. Now, this is an important point, that for getting the solutions through linearization, we need the terms of degree 3 and 4 must be absent in the invariant. So, this is completely, I mean, we are strictly following this restriction throughout our discussion. So, once you assume this, the invariant reduces to this form, and again through the linear transformations one can transform this to the canonical form of this form. And this reduced form can be parameterized in terms of trigonometric functions, where x and y as given by this, with this a and phi is given by this. So, now this classification of linearizable mapping obtained from QRT is by assuming A1s through various choices of A1s. I mean, it has been done by Grammaticos et al. So, we have these classes of linearizable systems, and here I would like to remark that once you have A1 is fixed, we have the left hand sides are fixed, left hand side of these equations are fixed, and in the case of right hand side, we observed, this is not a theorem, but we observed that in the A matrix, if the triangular, I mean corners of the matrix, 3 corners are 0, the linearizable systems can be obtained. This is only in observations, either top corner or down corner or this corner, all the 4 corners, or the 3 parameters should be 0. So, with these type of observations, we could able to classify or list these canonical equations, additive type, multiplicative type, or p-phi type, or various forms, and these forms followed from the forms of the discrete Paine-Levé classifications also. So, our guidelines is from discrete Paine-Levé, but for linearizable systems we restrict the parameters in the A matrix such a way that we could able to get. So, this goes to all the way to the E8, E7 classes also. That means, in fact, linearizable equations is really huge in this setup. And also you observe that the right hand side is either quadratic by quadratic, quadratic by linear, linear by quadratic, linear by linear. So, you can choose various forms on the right hand side also. So, now we are going to discuss about this through autonomous level and the non-autonomous level as well. As we know very well that I mean at least our group follows two strategies to find the linearizability or integrability. One is through singularity confinement approach combined with algebraic entropy approach. So this is our strategy to analyze these type of equations. So now the conjecture all the S integrable systems satisfy this singularity confinement criteria. C integrable systems may or may not satisfy the singularity confinement criteria. For example, all projective mappings satisfies the singularity confinement criteria. On the other hand, Gambier system may or may not satisfy the singularity confinement criteria, and the third kind never satisfies the singularity criteria. But however, you notice that all these three families are linearizable. We can explicitly linearize them and also find the solutions. So this is the situation here. And the other integrability detector is the well known algebraic entropy introduced by Viale and Eternita, and also this is not a theorem again, of course, and the epsilon is not 0, then the growth is exponential if the growth is polynomial for integrable systems, and more interestingly for linearizable systems the growth is linear in degree, and for integrable second order mappings the QRT type degree growth should be quadratic. For projective mapping, again just to compare as in the case of singularity confinement, projective mapping the linear growth of course is possesses singularity confinement. Generic Gambier mapping is exponential growth. Certain subclass of Gambier mapping growth stops means a stage as such, and third kind mapping grows in steps 2. It goes I will give an example for this. So even though they never possess singularity confinement, we have a growth property. Here also we have a growth property whether pass the test or not pass the test. Okay. So let us take the Gambier mapping of this class. The degree growth is 0, 1, 2, 2, 2 stops after certain level. And if you take the third kind mapping, here this mapping you can this never pass the singularity confinement, but the degree growth is 1, 3, 5, 7, 9, etc. So the degree doubles. So with this background, we now go to integration of these linearizable mappings. So consider the Gambier type equations and introduce the Riccati sum Riccati through these transformations z in terms of x, and it reduces to linear equations, the solution of which can be constructed through the solution of the Riccati. Therefore, the solution of this equation can be obtained explicitly. Now, what about the third kind mapping? There are two third kind mapping we consider here. One is the right hand side is quartic, another is quadratic, and this is of P type, P5 type, another is multiplicative is the P3 type. Now, we show that first we will take this is a pure constant, this may be a function of n. So, at least one parameter should be pure constant. So, take now we consider the discrete derivative with respect to b, that means upshifted this and then cancel the b, I mean eliminate the b, we will get an equation like this. And now we consider the linear map of this type, and if you take the discrete derivative of this linear equation, again this should be same as this equation. So, now the solution of this as can be obtained in the following way. Say x naught x 1 the initial conditions are given, use these initial conditions in the nonlinear equation, we get x minus 1. Now, we have x naught x 1 and x minus 1, use all the three values in the linear equation, and then obtain the value of k. Once you know the k, we can solve this linear equation, and therefore, the solution of this equation can be obtained. Of course, one can obtain the invariant for this equation also. The similar thing can be obtained for the other quartic polynomial on the right hand side. Now, let us consider this here the QRT invariant without, I mean only in the quadratic in degree. Therefore, we autonomous, this is autonomous form. Therefore, we just substitute this answers, and then we can say this is exponential form, and when you substitute this equation, we will get all the values of P and R. And also this is now in the case of autonomous, it is quite easy, but in the case of non-autonomous, it is quite difficult, because we have to adopt a different strategy. For example, we consider these non-autonomous equations, transform this equation to this equation, and now we make this answers the solution of this equation, where phi satisfies the same exponential type of solutions. And now, even though the presentation is we gave the explicit solution first, but the strategy is that always consider the nonlinear system and linear system, also this linear system, and demand this phi also should satisfy this. That means, you put in some unknown function here, and the linear system linear system here. So, using the invariant of the quadratic invariant. So, using all the three information together, we have to find the proper invariant, proper denominator in the linear equation, and also for the this part. So, once you have this consistently all the relations, we can able to solve the linear system and get the solutions in this form. So, the same strategy has been applied to many systems, for example, this equation as well, and the linear system corresponding to this is given by this, and the invariant is given by this, and solution can be computed explicitly like this. So, start with the nonlinear system, and once you obtain the linear system, which could be able to solve, and this linear system and the nonlinear system and the invariant should be consistent. That is the first point. We could be able to get the solution explicitly. Now, what happens to the this case? For example, if you consider this case, third kind, and this equation is related to the Gambier type. This is a function of the Z only. Therefore, some of the equations of third kind are related to the Gambier type, where some of them are not. This is again equation which can be related to the Gambier type, but some of the third kind equations are not related to Gambier type also exist. So, integration is as I explained the same way. So, all third kind mapping or derivatives of Gambier are connected with the Gambier equations, and this example shows that this is not the case. So, there are a lot of calculations are there, but however, we could not be able to show that this is not connected to Gambier equations. No relation to the Gambier equation exists for this case. What happens to the classes of higher third kind linearisable mapping? If we take equations from E8, E7 also of these complicated situations, even though these singularities are not confined, this type of anti-confining singularities or weak singularities in the terms of technical sense, but in the algebraic geometry sense they are confined, and these equations also can be linearized. We can have a QRT invariant and solution can be obtained, and through the same approach which I described earlier. The associated linear equation is lengthy, therefore, I could not be able to display it. Another example again is that same situations, solution could be obtained explicitly, invariant can be obtained, and the linear equation is given in this form, and phi is satisfies this. And these higher equations also, they are related to Gambier type of Gambier. It comes under the Gambier class. So, all the equations of the Gambier higher equations also, they reduce to either this or this is a trivial one. So, having the mapping obtained from dp through a limiting procedure, the autonomous limit Gambier must be of the only non-trivial QRT mapping known to be of Gambier type of this form. So, we have shown that the equations which I described earlier reduces to this form. Conclusion is that the non-autonomous third kind mappings, a free function always exists. We can also notice that in the Gambier type, we always have a free function, arbitrary function of n, and using the singularity conformity is difficult in this case, but of course, we have a linear growth in this case, and which ensures that they are linearizable. And subclass of third kind mapping may be belongs to Gambier mapping, and some of them are not. So, why only subclass related to Gambier is not clear. All the Gambier mappings can be transformed to the same form which I explained earlier, and the results presented here can be extended to asymmetric case, that is the linearization procedure obtaining the solutions, and also the coefficients can be of periodic coefficients instead of usual one. So, these are the things.
Questions, remarks?
I want to know what one thing.
Sorry.
Oh, sorry.
You said Gambier mappings, the degree growth of Gambier mappings are exponentially.
In generic,
Right.
generic.
But in my knowledge, at least, Gambier mappings reserves rational fiber. So that means degree growth should be linear. And the next point is the third type.
Third kind.
Third kind is also has linear growth.
Yeah, linear growth is third kind is yes. Yeah.
That means the third kind also preserves rational fiber. So
Yeah.
it's very almost the same in the same classification.
In the Gambier map, even though the singularity pattern is a weak singularity, what we call a weak confinement or anti-confining, but in the terms of algebraic geometry, by using the transformations, it can be regularized. It was proved by Fever. So, in that sense, it is confined singularities.
Unconfined.
Gambier.
Gambier singularity. Gambier does not have singularity.
No, in our sense, it is not confined. In the sense of algebraic geometry or Fever, it is confined.
You mean?
Yeah. So, what they say that if the singularity pattern is infinity throughout and regular at the middle, this is okay. If the pattern is in the third kind mapping, the pattern is infinity, infinity square, infinity cube, etc. So, this is never be confined. So, that's
No, I was going to ask the same question actually. So, thank you.
so the same.
Other questions, please? Okay, seems to be not the case. Thank you again.